Now that you have explored the first three layers of the OC model, physical, data link, and network, you have seen how data travels as electrical signals, how Ethernet frames are built, and how routers forward packets across networks using IP addresses. You have even traced the path of a packet to a real website using traceroute. It is now time to go one level higher and explore Layer 4, the transport layer. This is where two of the most important protocols in networking live: the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. Understanding the differences between these two protocols is fundamental for any cybersecurity practitioner, because many attacks, detection techniques, and defensive configurations are directly based on how TCP and UDP behave. The transport layer sits just above the network layer. While the network layer is responsible for routing packets from one machine to another across multiple networks, the transport layer is responsible for managing communication between two applications running on those machines. Think of it this way: IP gets the data to the right computer, but TCP or UDP makes sure the data reaches the right application on that computer and handles how reliably it gets there. To understand this, you need to know about ports. A port is a numerical identifier, from 0 to 65,535, that specifies which application or service on a machine should receive the incoming data. For example, when you visit a website, your browser communicates over port 80 for unencrypted hypertext transfer protocol, or port 443 for encrypted hypertext transfer protocol secure. An email client sending mail might use port 25, simple mail transfer protocol. A domain name system resolver listens on port 53. Ports allow a single machine to run dozens of services simultaneously, each on its own port, all sharing the same IP address. Both TCP and UDP use ports. The fundamental difference between them lies in how they handle the delivery of data. TCP, the Transmission Control Protocol, is a connection-oriented protocol. This means that before any data is exchanged, TCP requires both parties, the client and the server, to establish a connection through a process called the three-way handshake. Here is how it works. The client sends a segment with a flag called SYN, short for synchronize, signaling that it wants to open a connection. The server responds with a segment carrying both SYN and ACK, acknowledgement, flags, confirming that it received the request and is ready to communicate. The client sends a final ACK segment to confirm that it has received the server's response. Only after this three-step exchange does actual data transfer begin. This handshake ensures that both sides are ready and reachable before any payload is sent. Once the connection is established, TCP provides several guarantees. Reliable delivery. Every segment sent by TCP is acknowledged by the receiver. If no acknowledgement is received within a certain time, TCP automatically retransmits the missing segment. No data is silently lost. Order delivery. TCP assigns sequence numbers to every byte of data. Even if segments arrive out of order, which can happen because they travel different paths across the internet, TCP reassembles them in the correct order before passing the data to the application. Error detection. Each TCP segment includes a checksum to verify data integrity. If a segment is corrupted in transit, it is discarded and retransmitted. Flow control. TCP regulates how fast data is sent, so that a fast sender does not overwhelm a slow receiver. The receiver tells the sender how much data it can currently accept, called the receive window. Congestion control. TCP also monitors network conditions and slows down transmission if it detects congestion on the network, helping prevent network collapse. A practical example of TCP in action. When you load a web page, your browser opens a TCP connection to the web server, performs the three-way handshake, then requests the HTML file. The server sends the file in multiple segments. If any segment is lost along the way, TCP ensures it is retransmitted and that the browser receives the complete, correctly ordered file before rendering the page. To close a TCP connection cleanly, a four-step process is used. The initiating side sends a finish segment, the other side acknowledges it, then sends its own fin, and finally receives an acknowledgement. This ensures both sides agree that the exchange is finished. UDP, the User Datagram Protocol, works in a completely different way. UDP is a connectionless protocol. There is no handshake, no acknowledgement, no guaranteed delivery, and no ordering mechanism. A sender simply packages data into a unit called a datagram and fires it at the destination. If it arrives, great. If it does not, UDP does not notice and does not retransmit. This sounds like a weakness, and in some contexts it is. But UDP's simplicity is also its strength. Because it has almost no overhead, UDP is extremely fast and lightweight. It is ideal for use cases where speed is more important than perfect reliability, or where the application itself can handle occasional data loss. Concrete examples of UDP in use. Domain Name System (DNS) queries. When your computer asks a DNS server to resolve a domain name like example.com into an IP address, it uses UDP on port 53. The query is tiny, the response is tiny, and if no answer arrives, the application simply retries. There is no need for a full TCP connection overhead. Video streaming and voice over Internet Protocol (VoIP). In a video call, a few lost frames or audio packets do not matter much, you will barely notice a tiny glitch. But if TCP were used and it tried to retransmit every lost packet, the delay would make the call unusable. UDP lets the stream continue in real time, accepting minor losses. Online multiplayer games, game state updates, positions, actions, must arrive as fast as possible. A slightly outdated update is better than a delayed one. UDP is used here so that the game does not freeze waiting for retransmissions. Streaming protocols like Real-Time Transport Protocol, RTP. This protocol, used for audio and video transmission over networks, runs on top of UDP precisely because low latency matters more than perfect reliability. Now let us compare the two protocols side by side to consolidate what you have learned. Connection setup. TCP requires a three-way handshake before sending data. UDP sends data immediately, without any prior negotiation. Reliability. TCP guarantees delivery through acknowledgements and retransmissions. UDP offers no such guarantee. Order of delivery. TCP ensures data is reassembled in the correct order. UDP does not maintain order. Speed and overhead. TCP is slower due to its connection management and error handling mechanisms. UDP is faster because it has minimal overhead. Use cases. TCP is used for web browsing, Hypertext Transfer Protocol, Hypertext Transfer Protocol Secure, Email, Simple Mail Transfer Protocol, Internet Message Access Protocol, File Transfer Protocol, and Secure Shell Access, Secure Shell. UDP is used for DNS, real-time video/audio, game traffic, and network monitoring protocols. From a cybersecurity perspective, the differences between TCP and UDP are critically important. Many attack techniques exploit the specific behaviors of these protocols. TCP SYN flood attack. An attacker sends a massive number of SYN segments to a server, pretending to want to open connections, but never completes the handshake. The server allocates resources for each half-open connection and eventually runs out of capacity, making it unable to respond to legitimate users. This is a classic denial of service attack that exploits the TCP three-way handshake. TCP port scanning. Tools like Nmap use TCP's handshake behavior to discover which ports are open on a target. By sending SYN segments to many ports and observing whether the target responds with SYN ACK, port open, or RST, reset, port closed, an attacker or security auditor can map the services exposed by a machine. Understanding TCP handshake behavior is therefore essential to interpreting Nmap scan results. UDP port scanning. UDP scanning is trickier because there is no handshake. Nmap sends a UDP datagram to a port. If it receives no response, the port might be open and silently accepting data, or a firewall might be dropping the packet. If it receives an Internet Control Message Protocol port unreachable message, the port is closed. This ambiguity makes UDP scanning slower and less reliable than TCP scanning. Firewall and intrusion detection rules. Many firewall rules are written based on TCP flags, SYN, ACK, FIN, RST, or on specific UDP port numbers. A security analyst who does not understand these protocols cannot correctly write or interpret these rules. Session hijacking. Because TCP assigns sequence numbers to each segment, an attacker who can predict or observe these numbers could potentially inject malicious data into an established TCP session. This is known as TCP session hijacking and represents a real threat in unencrypted environments. Reconnaissance and fingerprinting. The way a system responds to unusual TCP flag combinations, such as a segment with all flags set, called a Christmas tree packet, or a segment with no flags set, called a null scan, can reveal information about the operating system. This technique, known as OS fingerprinting, is used both by attackers and by penetration testers. Finally, it is important to know that both TCP and UDP can be encapsulated and encrypted. The Transport Layer Security Protocol, TLS, runs on top of TCP and encrypts the content of TCP segments, which is why HTTPS is secure. More recently, the QUIC protocol, used by HTTP version 3, runs on top of UDP and also applies encryption, combining the speed of UDP with modern security guarantees. To summarize the key ideas of this chapter, TCP is a reliable, connection-oriented protocol that guarantees ordered and complete delivery of data through a three-way handshake, acknowledgements, and retransmissions. It is used when data integrity matters more than speed. UDP is a fast, connectionless protocol that sends data without guarantees or overhead. It is used when speed and low latency matter more than perfect reliability. Both protocols use port numbers to direct traffic to the correct application on a host. From a security standpoint, TCP's handshake mechanism is the basis of many attack techniques: SYN floods, session hijacking, port scanning, and defensive measures. UDP's lack of state makes it useful for fast services but also creates challenges for scanning and detection. Tools like Nmap and Wireshark, which you will use extensively in this course, rely heavily on understanding TCP and UDP behavior to perform network discovery, vulnerability scanning, and traffic analysis.